So thanks very much. I've got the graveyard shift today, so I'll try and be entertaining and build on some of the really enlightening conversations that we've had up until now. So the topic of conversation for the last hour or so obviously has been sustainable manufacturing, circular economy, how we can really make machines for future production more sustainable. So today I'm going to give a brief overview of three main areas: materials, manufacture and remanufacture. Just give some examples and some of the drivers for why we need to change. So obviously everybody's aware that the requirements for electrification solutions are really becoming more and more prevalent as the months go on in order for us to meet net zero targets. Within FEMM Hub, we're looking at key markets, including electric vehicles, more electric and all-electric aircraft, and as we've heard earlier as well, wind turbines are only increasing in power and size. So growth of these markets really is essential in order for us to meet the net zero targets, not only from the UK government, but from governments worldwide. However, the rapid development of these markets, if we continue with the manufacturing processes that are currently done, are really unsustainable in the long term. So it's how, I'm glad Dave put it in there, how we make sustainability really a key focus of future design and how we make it not an afterthought, but an integral part of the conversation going forward. So I'm going to touch on these three topics, first one of which is going to be materials. So, as you're all probably aware, the supply of key materials for electrical machines, some of the material types are threatened and some of them have limited availability. So, on the table there, some key components, the materials of interest, and you can see some of them are not currently threatened, but more than half are either have limited availability or have increased threat to supply. And obviously, securing future supply routes for these materials is going to be critical for us to be able to meet the production demands. Virgin material production obviously is a truly global activity at the moment, but if we can potentially make use of the materials ready within the UK, we can not only localise material supply but also help de-risk some of the supply chain issues that we've got. So this is some information from the International Energy Agency. They did a report on critical minerals for clean energy transition, so transitioning away from fossil fuel energy supplies to some of the greener solutions. So you can see some of the key materials require production, which they're forecasting for the 2050 net zero targets, and then the known reserves of some of these key materials. So you can see the known reserves go from adequate reserves down to less than 3.5% of what we actually think we'll require for future production. And then in terms of the location, so we've got neodymium magnets on the left-hand side and steel alloy on the right, and you can see the range of elements that are included in the production of these particular materials. And we've got a list of the likely places of origin, so the most common places that these come. So you can see from a global perspective, they're coming from all over the world to a centralised location, either in Europe or Asia, and then they're coming to the UK in order to be in use. So one of the key questions is how can we retain some of the high-value materials that we've already got in the UK? How can we make use of them? So more generally, we talked about recycling as on the hierarchy of circular economy principles, and recycling is a really important aspect of maintaining these high-quality materials. So aluminium, for example, it's estimated that of all the aluminium ever produced, 75% of it is retained in circulation to this day. And when you're talking about recycling aluminium, it uses 95% less energy than when you're talking about virgin material production. And recycling 1 tonne of aluminium saves 8 tonnes of the raw bauxite and 9 tonnes of CO2 emissions. So you get huge savings on multiple fronts. From steel point of view, again, recycling of steel helps you reduce CO2 emissions by 80% compared to new steel from raw materials. You also get huge decreases in water consumption and water pollution by recycling the material. And there's already examples of recycled steel within industry at the moment. So apparently, roughly 70% of a car's weight comes from the steel within the frame, and every new car that's made today has about 25% recycled steel content. So good improvements, but how can we take that further? And then obviously copper, which is a key material for us in electrical machines. Premium grade scrap copper holds around 95% of its value to virgin materials. So when we talked, quite often when you talk about recycling material, you get degradation of properties and loss of value as well. But copper really maintains a lot of its value. And obviously, as we all know, due to its good conductive properties, it's used a lot in electrical applications. Approximately 65% of the copper in the world gets used in electrical applications, so we've got a huge opportunity to make good use of it. And again, like aluminium and steel, recycling copper allows for 85% energy savings, a cut in CO2 emissions by approximately 65%, and again, similar to aluminium, apparently 80% of all the copper that's ever been mined is currently still in use today. And again, Europe's already in a reasonably healthy situation in that apparently roughly 42% of the copper which is used in Europe comes from recycled sources. So again, we're in a good position, but how can we improve that? So recycling of material really comes to the forefront when you think about, I'm going to use wind turbines as an example just because the sheer volume of materials that we're talking about in this industry. So by 2035, it's expected that there's going to be 3.8 gigawatts of offshore wind capacity within the UK that's going to have to be decommissioned. And then by 2066, we're talking about almost 5,500 wind turbines. And when we think about the materials that are within the 2035 estimate, I should say that these materials are for the entire wind turbine. Like Michael said, it's quite difficult to get specific data on the electrical machines, on the generators. So this is for the whole turbine, but hopefully it'll give you an idea of the estimates of material. So by 2035, for the decommissioned wind turbines, we're talking over 1 million tonnes of steel, 635,000 tonnes of concrete, 117,000 tonnes of ductile iron, 7,000 tonnes of neodymium from the rare earth magnets, and 5,000 tonnes of copper. And when we think about that in monetary terms, it's estimated that the value of the recycled steel is going to be worth up to 3.2 billion to the UK economy, and the value of the recycled copper is going to be 166 million. So large numbers for the material and large numbers for the value as well. So with the decommissioned material, why do we need to make use of it? Well, Michael touched on what we're expecting projections for future manufacture. And in the wind turbine for Scotland, we've got offshore capacity of 3.5 gigawatts, and that's from 432 turbines. But there's currently already authorised content for an additional 6.6 gigawatts on top of that. And if we look at what is going to be needed for the offshore wind by 2050, it's approximated that we're going to need very high numbers of materials, so almost 15 million tonnes of steel. Again, this is for the entire turbine, not just the generator. But when we're talking about copper, which is predominantly going to be from the generator, 67,000 tonnes of copper. So it's an awful lot of material. So what we need to do is with the wind turbines that are going through the decommissioning phase, how we can get the right strategy to make use of that material. Like Michael said, there's not going to be enough virgin material content, so how we can make use of the decommissioned material to help ease the burden on the future manufacture. And then in terms of the recycling for the future materials as well, so this is a sort of breakdown of the materials that are going to be required for the turbine for 2050 and the typical mass percentage that they've got within the turbine. If we then think about the carbon content of the production of the material, you can see we've got primary carbon content and recycled carbon content, and there's a huge discrepancy. Obviously, the recycled carbon content, much lower in terms of CO2 emissions. Like I said, this is for the whole turbine, so if we focus, say, just on copper, it's estimated that we could have an average carbon saving of 82% if we can use recycled material instead of the virgin. So in terms of being able to retain the key materials in the UK, it's beneficial on multiple fronts. It makes efficient use of the materials that are already here. We can reduce the carbon emissions through the recycled materials rather than new material production. We can ease the burden, because there is going to be a burden as values in volumes of manufacture are increasing, how we can ease the burden on virgin material production. And also there are, at the moment, supply chain risks with certain materials, and I think that's probably going to increase as we're going forward, as everybody's going to be fighting over the same stock. So the fact that we've got so much material already in the UK, how we can make best use of that. So from a manufacturing point of view, I'm going to go through two very quick case studies. Unfortunately, they're not electrical machine specific, but hopefully it gives you a flavour of some of the things that we can do just by changing the manufacturing that we're looking at. So the first one is a flow forming case study. So flow forming is a near net shape manufacturing process where essentially you make axisymmetric tubes. So you start with a tube which is short in length, thick in wall section, and then you form it out something which is longer in length and it's got a thinner wall section in it. So one of the projects I worked on a few years ago was looking at engine shafts for aerospace, and typically that shaft would be produced with a solid forged bar, which is then machined down to its final dimensions. And we looked at flow forming as an input, as a forming process for that, and we found that if we use forged bar as an input to flow forming, we could save up to 60% of the input material for that particular component. We then tried to take it one step further, so you can see the image at the top there is centrifugally cast tubes. So it's a high quality casting process, which again gets you axisymmetric tubes. We used the near net shape preform as an input to the near net shape manufacturing process, and we estimate that we can save up to 85% of the input material. So instead of having your bulk forging, which you're machining and getting swarf for recycling, you're limiting how much material you're putting in, and you're getting a near net shape entire processing route. So things like flow forming, centrifugal casting as well has additional benefits that you get the cast coming out, and then it gets machined in the foundry. So basically you get your near net shape preform with the machining done in the foundry, so it's easy recycling. So the swarf from the first batch can easily get put into the next casting operation. You don't have to go through a really hard difficult recycling process. You're doing it all in-house. And with things like flow forming, you're also reducing the processing time. So we looked at, say, an engine shaft for an aerospace component, and the production time for a solid forging to be fully machined can be anything between 2 and 3 weeks. So it's very intensive, takes a long time. Whereas something like the near net shape processes, we can reduce that to about 2 or 3 days from raw material to final component. So you're reducing your process time, because the flow forming operation specifically is done at room temperature. You're using less force than traditional methods. So some of the cold forming techniques take as little as 20% of the force of a sort of traditional forging operation. And because you're doing it at room temperature, you're reducing your energy consumption during the manufacturing process as well. So just by reassessing how you can manufacture the component, you're saving on your material, you're increasing your potential for recycling, reducing your process time, and reducing your energy consumption during manufacture as well. The second case study is to do with metal spinning. So this was a project that I did, which was funded by the European Space Agency, that I did with Airbus. So we were looking at the method of manufacture for propellant tanks. So the images that you see on the top are two different geometries of propellant tanks that get often used within space applications. And their method of manufacture at the start of the process was a titanium dome, which was forged and then fully machined away. So again, you're talking about bulk forging with a lot of machining. So you've got high material wastage and high production costs with that. So we were looking to use a process called metal spinning, which basically takes a flat blank and then you spin it into a dome shape component. And again, like flow forming, metal spinning is done at room temperature. So you actually refine the grain structure of the material. So you improve your mechanical and your fatigue properties. And what that allows you to do, because you've got a stronger component, you can actually swap out your material for cheaper materials, essentially. So what we looked at, rather than spinning of titanium, we were looking at spinning of aluminium. So lighter materials, well, often you can do a swap for lighter and also cheaper materials because you're getting the benefits of specific manufacturing processes. So the images that you see down the bottom are the spun domes that we did for the project. And at the completion of the project, these domes successfully passed a TRL review, technology readiness level, up to TRL 6, which is the stage basically just before implementation. And Airbus expects to see their cost savings in the region of around 30%. Again, focusing on the method of manufacture and how you can get huge improvements just with very slight changes. So the changes in method of manufacture, again, if you take a step back from always doing it the way that it's been done, if you look at what you actually require from the component itself, changing the method of manufacture can lead to large material savings, reduction in processing time, energy consumption. Like we see with the metal spinning, you've also got opportunities for lightweighting, depending on the method of manufacture that's chosen, which can then allow you to make subsequent material swaps. And also with the advances that we're seeing in the manufacturing sector, so we heard quite a lot about additive manufacturing earlier, but some of the other processes like flow forming, like spinning, they are really opening up the opportunities for what we can do in the design space. So how we can take advantage of the changes that are happening in the manufacturing sector and actually make things or make different types of components. The final thing that I wanted to touch on, Dave introduced it a little bit earlier, is remanufacture. So like Dave mentioned, remanufacture is different from repair in that you've got more quality in it, essentially. So with repair, you're typically doing something which is quite quick and it will last as long as it lasts. Whereas with remanufacture, like Dave says, you're stripping things down, you're doing testing, you're swapping out components, and then you're putting everything together and you're putting a warranty on that component, so it's an as-new material, an as-new assembly. So remanufacture's got a host of environmental benefits. It reduces the demand for newly manufactured products and virgin material as well, which, as we've seen, is very carbon intensive. Recycling, which I introduced at the start, is an option that we should definitely be using, but remanufacture has got much better environmental outcomes than it is. As Dave mentioned, the hierarchy, the further up the hierarchy you are, the better it is from an environmental point of view. You could reduce transportation as well, because typically things are remanufactured in the area that they're in use, so you've not got so much transportation around the globe. And in terms of things like environmental legislation, the remanufacturing supply chain, it allows you different opportunities to be able to bring environmental legislation into an application and make sure it's adhered to. But from an economic point of view, obviously cost is really still a key driver in every industry that we're talking about. You can often see huge cost reductions. So Zero Waste Scotland said that in general for remanufactured equipment, you can see between 34 and 60% cost reduction, so very significant in some ways. And as I mentioned earlier, with the recycling of material, remanufacture also gives you more insulation from supply chain disruption, gives you a lot more control over the components and where they are at any given time. And something that probably often gets overlooked is the development of a remanufacturing process for a particular component can increase the residual value of that equipment or that component as well. And being able to increase the residual value of individual components or an electrical machine assembly, it encourages different purchase decisions in the longer term as well. So you get away from just looking at the cost and actually looking at a whole array of things, from quality of the components and longevity of them, as in addition to the cost. So it's a more rounded point of view. So unfortunately, I don't have any very specific remanufacturing case studies for electrical machines, but these were the ones that I could find that were in the same ballpark. So remanufacture of a starter, an alternator. In terms of the energy consumption, so if we assume the new component takes 100% energy, the remanufactured starter took 9% the energy required, and the remanufactured alternator took 14%. And then in terms of material consumption, again, assuming 100% for the new component, you're talking about 11% for the starter and 12% for the alternator. So huge reductions on both energy and material. And then in terms of Caterpillar, they did a remanufactured cylinder head. I'm not going to go through it, but you can see everything from water use, energy, waste sent to landfill, everything's got huge amounts of reduction. And then in terms of repair and remanufacture, what we're looking at is targeted solutions. So we looked at additive manufacture earlier as a primary manufacturing opportunity. But one of the things that we're looking at in the FEMM Hub is how we can use something like additive as an optimal secondary operation, so targeted repair and manufacture. So the video that you can see running is a gear tooth. It's a project that we did within AFRC a few years ago. So you get a gear tooth where you've got one gear, one tooth which is damaged. So rather than scrapping the whole gear, you machine away the damaged tooth, layer it back up using additive manufacture, and you do a final machining operation, which you can see on the right-hand side to get it back to tolerance. So again, how you can target structures to save your material, get reduced processing times, and save cost overall. So that was a sort of small demo that we did within AFRC. There's a company in Scotland called Reiki Manufacturing who do this in practice. So they, rather than working on an electrical machine, they work on the yaw gear, which is within the red box that you can see. So it's right in the middle of the turbine. It's really difficult to get to. And typically, if the yaw gear gets damaged, you have to remove the entire rotor and the seal, remove the damaged component, and then replace it and reassemble everything. So obviously doing this, especially if you're talking about offshore wind, you've got a lot of issues in terms of craneage, access to the turbine, craneage, and then complex lifting operations, whereas they do in situ machining and additive manufacture for repair, which gets you reduced material consumption. So they're approximating 80 to 90% material savings because they're not taking the whole yaw gear out and removing it. And also because they're doing it in a very limited way, that they can easily capture that material and recycle it. And then obviously with offshore as well, your schedule time reduction. If you're going out in a boat, you're waiting on weather to be advantageous for you. You've got cranes, you've got a lot of lead time and a high cost to repair. So this sort of targeted, localised, in situ repair and remanufacture, I think is something that should be, can provide huge benefit going forward. So I got my, my 1 minute warning. So basically, in summary, what I was trying to get at with this talk is that the circular economy doesn't dictate one approach and one solution. It's an alternative way of looking at the problem that we're currently facing. And I think for us to find truly sustainable solutions, it's not going to be a silver bullet, it's not going to be one size fits all, but it's about making small changes from everything from the design, the manufacture and the remanufacture, the whole life cycle, how those small changes all add up to large changes over the whole life cycle of the machine. Material choices are going to be critical to reduce cost and CO2 emissions. Thinking differently about how you manufacture the components will again lead to material and cost savings as well as reduced processing times. And how can we actually implement strategic repair and remanufacturing activities so that we can enable asset life extension going forward. And all of this hopefully will add up to a more sustainable future. So I think I'm just on time, but thank you very much.